Hello, it is Mrs. Scarple, and this is the third lesson of Unit 1 on quadratic functions. This lesson has a focus on modeling a quadratic function with tables, graphs, and equations, just like we've done with the two previous lessons. We're also going to be focusing on that first difference of a quadratic function and how a quadratic function can be built from a linear function. So really this is just more practice on what we've been doing in the prior lessons. So here's our situation today. Scott was determined to eat right and get in shape. He joined a gym and added push-ups to his daily exercise routine. He started keeping track of the number of push-ups he completed each day in the bar graph, with day 1 showing he completed 3 push-ups. After 4 days, Scott was certain he could continue this pattern of increasing the number of push-ups for at least a few months. So we have day 1 has 3 push-ups, day 2 has 5, day 3 has 7, and day 4 has 9 push-ups. We're going to take this pattern and we're going to model it using both a table and a graph, and we're going to write the explicit and recursive equations. So here is our pattern that we start with, and we have days 1, 2, 3, and 4, and we're going to see if we can see the pattern and complete days 5 and 6 without having to draw them out. So we know that day 1 has 3, day 2 has 5, day 3 has 7, day 4 has 9. So let's look at our first difference here. Remember, the first difference is just finding how are we increasing from one number to the next. So from 3 to 5, that's adding 2. From 5 to 7, that's adding 2. From 7 to 9, that's adding 2. So if I want to continue the pattern, I see that we just keep increasing by 2. So 9 plus 2 is 11. 11 plus 2 is 13. So let's graph this. N is the day number, so I'm going to label my x-axis, which is my n, day number, and I'm going to label the y-axis number of push-ups. I want to remind you that function notation like f of n is just another way of saying y, and because this is f of n, we can say that our n is like saying x. Put a scale on my graph. It's going to start at 0, and I'm just going to go up by 1, and I'm going to go by 1 as well on my y-axis. Only so it doesn't seem so crowded, I'm going to label every other one. And then plot the points. So day 1, Scott did 3 push-ups. Day 2, he did 5. Day 3, 7. Day 4, 9. Day 5, 11. And day 6 was 13. And if we look at these points, what you should be seeing is they're increasing. They're going up by the same amount and going to the right by the same amount. So we have a slope of 2 over 1. So this is a linear pattern. So what we have is a linear function. I'm going to start by writing the recursive formula for this linear function. A recursive formula, you always start with what is the first value that we know of. So f of 1 equals 3. And then we write what we're doing to get each term. So to get f of n, to get the next value, I take the previous value, and as we look at our pattern here, we're increasing by 2. So this plus 2 that we have, when it's a linear pattern, you're going to have f of n equals f of n minus 1, and then you're going to just write what that constant difference is. In this case, that constant difference is 2. For the explicit equation, because this is a line, our explicit equation is going to be similar to y equals mx plus b. We're just going to be using function notation instead. So the y is f of n equals, I'm going to have some number n, because we said n is like saying x, plus another number, because a linear function takes on this form. Now, this number that goes before the n is like m. That's the rate of change. That's our slope, which is that constant difference. So I'm going to have 2n, and then what I need to find is what the y-intercept is. There's a couple of ways we can do this. We can look at the graph and go backwards to find a point on the y-axis. So that's going down to left 1, down to left 1. And we have our y-intercept is at 1. So I'm going to put a 1 here. If it's not so easy to go backwards and find that y-intercept on the graph, what I can do is I know that it's going to be 2n. What do I need to do to 2n to get this value of 3 for day 1? So instead of 2n, I should actually write 2 times 1, because n is the day number. So 2 times 1 is 2 plus 1 equals 3. Then for day 2, I would do 2 times 2 is 4. To get the 5, I have to add 1. Day 3, 2 times 3 is 6. To get 7, I have to add 1. So it does appear that the explicit equation is going to be f of n equals 2n plus 1. Now we're back to Scott at his gym, and the gym is sponsoring a muscle march promotion, and they're actually talking about the month of March. Make a note of that here. The goal of Muscle March is to raise money for charity by doing push-ups. Scott has decided to participate and has sponsors that will donate money to the charity if he can do a total of at least 500 push-ups. And they will donate an additional $10 for every 100 push-ups he can do beyond that. So now Scott is going to track the total number of push-ups done up to any given day of the month. So in class, I told the students to make an estimate of the total number of push-ups that Scott will do in a month if he continues to increase the number of push-ups he does each day in the pattern shown. I'm just going to go back to our table here to explain what's happening. So day 1 he does 3, day 2 he does 5, but that's a total of 8 for the 2 days. Day 3 he does 7 more, so 8 plus 7 would give us 15. So think about how that pattern is going, and just think about how many push-ups do you think Scott does in the month of March if he follows that pattern. Now, while you have that number, in class I had students estimate anywhere from like 158 up to 1,488. So it really varied. what we're going to do is we're going to go through some work and find out just exactly how many push-ups Scott could plan on doing during the month of March. So here we go. Draw a diagram that shows the total number of push-ups that Scott has done in the month at the end of each day. So if I take and I start drawing, we have day 1 will be 3 push-ups. That's how many he has done. Day 2, we take the 3 from the previous day and we add 2 more to get how many get added on. So I should say we're adding on the 5 for that day. Day 3, we have the 3 from day 1. We have the 5 from day 2. And then we have 7 from day 3. Day 4, we have 3 from day 1, 5 from day 2, 7 from day 3, and then we have 9 from day 4. And we could probably keep drawing this pattern, but it would be a little difficult to do so. So let's just see if we can see any sort of pattern here. We know we have 3 from day 1, then we have 3 plus 5, so 8 on day 2. 3 plus 5 plus 7 is going to be 15. And then we have 3, 5, 7, 9. So 15 plus 9 is 24. Now, in one of my classes, one of the students pointed out that I wouldn't need to keep drawing a taller column, but we could in fact draw rectangles. So day 1 would be the 3 rectangles, or the 3 squares in one column. But if we think about day 2, we could take this square that's on the top, cut it off, and move it down. So we'd have 2 by 4. And a 2 by 4 is also a total of 8. Day 3, we have a total of 15. So if I want to keep the 3 columns and I want a total of 15, I would need it to be 5 rows tall, because 3 times 5 is 15. And then day 4, keeping with the 4 columns, but just stacking them into one rectangle, I know that if I want to have 24 of them, I need to have 6 rows. And sorry, these last ones don't quite look like squares, but I think you've got the idea. We'll come back to these descriptions in a little bit, but let's see if we can take this pattern of 3, 8, 15, 24 and find how many that Scott would have done after a week, a full week. So I'm going to go to a table, and the first column is the day number. So we have 1, 2, 3, 4, 5, 6. We know from previously that the number of push-ups he did on day 1 was 3, on day 2 was 5, 7, 9, 11, and 13. I'm just going to use the next table, and I'm just going to call it the total. So we know at day 1 he had a total of 3. Day 2, we add the 3 and the 5 is 8. Add 5 to 7, or 8 to 7, excuse me, and we have 15. Add 9 to 15, we have 24. So that is our pattern so far. We know we had the 11, so I'd have to add 11 onto the 24 is 35. Add the 13 onto the 35, and we're going to have 48. So if we want after a full week, that's after 7 days. We know the push-ups are increasing by 2, so that's 15 more push-ups on day 7. 15 plus 48 is 63 push-ups. So we have a total of 63 push-ups at the end of 1 week. Is this getting really close to what you estimated, or did you choose something much larger? Let's graph this. So we have the day number, and then on the side we have total push-ups, or total number of push-ups. I'm going to need to adjust my scale this time. I'm still going to go by 1 across the bottom. We might as well include the 7. But I'm going to go by 5 on my vertical, but I'm only going to label every 10. So at the end of day 1, he had done 3 push-ups. At the end of day 2, it was 8. Day 3 is 15. Day 4 was 24. Day 5, 35. Day 6, 48. Day 7, 63. If we look, this is not linear. This is not going up the same amount. Instead, we have a curve. So if we look at our differences, the first difference, we already know what these numbers are because they came from the number of push-ups. 8 to 15, we added 7. 15 to 24, we added 9. We added 11. We added 13. And we added 15. Now this looks like our number of push-ups increasing. And we know that that difference is plus 2. This is what we call the second difference. So the first difference is not constant. We are going to say that this is actually linear because there is a pattern to the way it's increasing, but it's not a constant pattern. The second difference is constant. So now that we have this information, it's going to help us write our recursive formula and our explicit equation. So just like the last recursive formula, we have f of 1 equals 3. That's our starting position. We have f of n equals f of n minus 1. Now because this first difference is linear, what gets added on is going to be a linear expression. So like that y equals mx plus b, only it's going to be something n plus the b. We know that the constant difference of this pattern of numbers 5, 7, 9, 11, 13 is 2. So we place the 2 in front of the n. That's your rate of change, that's your slope. But now I need to find out what am I doing to the 2n, and remember n is the day number, to get my linear difference. So if I want to check on how I get this 5, I'm going to try 2 times 2, and what do I have to do to that to equal the 5 in my first difference? So 2 times 2 is 4, and then I have to add 1. Let's try it for day 3. To get the total on day 3, that's 2 times 6, but what we added to get day 3 was 7. That's also a 1. I'm going to try this one more time. 2 times 4 is 8. Plus 1 is in fact the 9. So that means my recursive formula is going to be 2n plus 1. And we call this a linear rate of change. And again, what we're doing is we're writing the expression that will give us this pattern for our first difference. With the explicit equation, as we've done in lessons 1 and 2, we've thought about this in terms of area. So I'm going to go back to our diagrams. I could just count the squares and I'd have my area in the first 4 that we did. But if I look at the second 4, I have rectangles. I have a rectangle that's 1 by 3, a rectangle that's 2 by 4, a rectangle that's 3 by 5, and a rectangle that's 4 by 6. One thing I notice is the number of columns, so my distance across, matches my day number. The other thing I'm going to speak to right now is, remember, area is length times width. So we're going to have n times my height. If I compare my height with my distance across the base, 3 is 2 more than 1. 4 is 2 more than 2. 5 is 2 more than 3. 6 is 2 more than 4. Since the 1, 2, 3, and 4 represent the day number as well, I'm going to have n plus 2. So we can say that to find the area of each of these rectangles, I'm going to take the day number times the day number plus 2. So let's go back to our explicit equation. We're going to have f of n equals n times n plus 2. And we can distribute this n times n is n squared. N times 2 is 2n. And this is our explicit equation. Again, thinking in terms of area. So, will Scott meet his goal and earn the donation for charity? Will he get a bonus? If so, how much? So if we take that explicit equation, f of n equals n squared plus 2n, and remember this is the month of March, and March has 31 days. So if I want to find f of 31, I'm going to do 31 squared plus 2 times 31. Remember, n is the day number. And 31 squared is 961 plus 2 times 31 is 62 for a total of 1,000. Let's see, 2 plus 1 is 3, 6 plus 6 is 12, carry the 1, 1,023 push-ups. So just over 1,000 push-ups for the month of March. If we go back and remind ourselves what it was a total of 500 push-ups plus $10 for every 100 push-ups beyond that. So yes, he meets his goal. And gets so 1,000 is 500 more than 500, and for each of those hundreds he gets $10. He'll get a $50 bonus. So what are our takeaways? One characteristic of quadratic functions is the first difference is linear, the second difference is constant. They are models for the sum of the terms in a linear function. We just showed that with our sum. The highest powered term in the equation is a squared term, like n squared. Equations can also be written as two factors, such as x plus 2 times x minus 3, or like we had n times n plus 2. Those are two linear factors. And they model situations with change in two dimensions, like area. So in our sum of our numbers, we kept adding to the width of our rectangle, but we also added to the height. Now it's time for some retrieval, some review. Multiply using the distributive property, then add like terms. So in lesson 1, we were distributing. So x times x is x squared. X times 9 is plus 9x. I have 2 times x and 2 times negative 2, so that's a positive 2x. Positive 2 times negative 2 is minus 4. Like terms, they have the same variable and they have the same power. So 9x and 2x would be like terms here. X squared plus, you just need to add the coefficients. 9 plus 2 is 11x. Minus 4 is our final answer. We can do the same thing with example 2. We're going to distribute. So 3x times 2x, that is 6x squared. 3x times 3 is plus 9x. When you distribute the 3 with your next set, distribute it as a negative 3. So negative 3 times a positive 5x is a negative 15x. And negative 3 times negative 4 is plus 12. When we look for our like terms here, it's the two terms in the middle. And we have 6x squared minus 6x plus 12. So that's multiplying using the distributive property and then adding like terms. This might not necessarily be so much review, but you're going to be asked to find the next or the first 5 terms of a sequence. And this is why we always give a recursive rule. So for example 3, the first term is going to be this negative 23. Our recursive rule says we are adding 4 to the previous term. So if I have negative 23 and then I add 4, this is negative 19. Add 4 again and we have negative 15. Add 4 to that, we have negative 11. Add 4 to that, we have negative 7, and the sequence would go on. But we're just being asked to give the first 5. For example 4, we're starting with 1. And this is saying we're taking 3 times the previous term because we have this 3 directly in front of it. So 3 times 1 is 3. 3 times 3 is 9. 3 times 9 is 27. 3 times 27 is 81. And the sequence would keep increasing in that manner. So this concludes lesson 3. I hope you find it helpful and that you can complete the Ready, Set, Go for lesson 3.